for 2 millennia around the Mediterranean. On the other hand, they also, these discoveries, these new things in the sky that we're seeing, were also crucial for going ahead and trying to complete the Copernican revolution, making a coherent picture of reality, which Copernicus didn't have, because the physics at the time was still the Aristotelian physics. Not because Aristotelian physics was a dogma, because it was best available at the time. And Copernicus changed everything. Aristotelian physics wouldn't fit with Copernican revolution. So Galileo gave, at the same time, a confirmation of Copernicus and tools with which Newton could bring everything together, this marvelous synthesis that is in his book, and the Principia, and which is the ground on which so much of modern science is based. Now, why I'm saying that? Because these things, black holes, are playing today a very similar role to what Galileo saw in the sky played at the time. These are a surprise for us, even for people who studied general relativity at school. I studied black holes at school when I was at university, except that the book was saying these probably don't exist. My teacher, so never believe in books that you study at school. Study them, because there was very good description of black holes, but then there was a conclusion was completely wrong. It was not a bad book, right? It was a fantastic book, written by one of the greatest scientists, Steven Weinberg, Nobel Prize, genius, and yet he had it wrong. So don't believe in books. What I was saying is that this incredible things, which are black holes, which the astronomers, like Galileo 3 centuries ago, have seen with this picture and with other. This is not the only evidence we have about black holes. We have a large amount of gravitational waves, radio signals, all sorts of astronomical things. Now we know these things are there. And we know that these kind of things are the best understood as what my book was calling black hole and was saying they don't exist, namely as a special solution of Einstein theory. And the beautiful thing is that, Einstein wrote this equation, 1915. He couldn't understand what is his own equation well. It took a long time to figure out what the equation predicted, but through many people, Schwarzschild, Finkelstein, blah, 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 Roger Penrose, and so on, it became more and more clear that the theory predicts these funny objects which are black holes. And these black holes would show themselves in some phenomena. One of these is this funny shape here. And now we have found all these phenomena, these rings and all sorts of the other phenomena. So black holes are a confirmation of Einstein theory, and at the same time, and that's where I wanted to get at, they are a tool and possibly our best door for going beyond general relativity and for telling something about this open problem, which is general relativity and quantum mechanics together. Because inside this black hole, or in the future of this black hole, there are precisely situations which cannot be accounted for, described with general relativity alone, nor with quantum mechanics alone. We need the two of them. So I want to tell you now two things. First, what we know about black holes, the solid part, the reliable part of our knowledge, up to the way where we go into the part we don't know. But that's the most interesting one, which is the one where quantum mechanics and general relativity come together. I spent my life in trying to build a theory of quantum mechanics and general relativity together, a theory of quantum gravity. So I will tell you about this theory and how it plays a role into black holes. Just before jumping toward the black holes and this explanation, one thing, careful, bringing together quantum mechanics and general relativity, completing the revolution, has nothing to do with the problem of writing the theory of everything, the final theory of physics, the unified theory of everything. These are two independent problems. The final theory of everything, well, who knows? my grandchildren, maybe. I think the universe is still too mysterious for hoping for a final theory of everything. We don't have a theory of everything. The attempts to write it down has found very bad no from nature. I think we're very far. There are so many things in the universe we don't understand. But the effort of putting together what we have understood about quantum mechanics, what we have understood about relativity, that's a whole problem that we have to solve. Good. So let's go toward this object, and let me tell you what we know and what we suspect about black holes. It's going to be my black hole. Because I needed something round. So a black hole is something round, essentially, whose size is, most black holes around us that we have evidence for are much bigger than this, but not too big. They're sort of a few kilometers, size of London, this London, where I spend most of my time, or Waterloo. But very, very massive. But the black hole much bigger than this, in fact, much, much bigger. This one, Sagittarius A star, is in the center of our galaxy. It's a million times bigger. So in mass, which is probably the size of, astronomical size, the size of the orbit of the Earth, I don't know, something like that. But there are black holes which are a billion times bigger, so colossal things, immense things. These are black holes we have evidence of. Maybe there are smaller ones. Maybe there are black holes of this size, or maybe teeny ones. We don't know. There's no reason for believing that they don't exist. If somebody says don't exist, remember my book that said no black hole exists, and just they have the size they are. They're very massive, right? So a black hole of this size would be more massive than the Earth. So to make a black hole, you have to squeeze a mass in a very, very small region. If we imagine we go there, and that's what I want to do. The title of this thing is coming into a black hole. I need your attention, your imagination, because this is going to be a trip of imagination, and also your being ready to accept that reality is very different than what usually look around us. So imagine that we're in a starship together. This building is a starship. We're flying toward a black hole. And say we're flying toward this one, which is one of the ones we know better because we have a picture of it. This is the center of the galaxy. This is Sagittarius A star. So we fly there, we go there, and what do we see? Well, basically, obviously, we see that, because